Over the course of the next videos, we'll go into much more detail about what we can do with Git. These are Git's greatest hits. We'll start by learning some handy shortcuts and looking into how we can get more info out of our version control system. Then, we'll experience the true power of Git by seeing how we can undo some of our changes. The ability to revert previous changes is one of the most useful aspects of version control systems. Depending on what needs to be undone, there's a bunch of different techniques that we can use in Git. We can discard the changes made to a file, fix a commit that was incorrect, and even roll back our project to an older snapshot. We'll look into all these techniques and dive into when to use each of them. Finally, we'll check out yet another important concept: branches. We can use branches to work on an experimental feature without affecting the main code of our project, support separate versions of a program that can't be merged together, and much more. We'll dive into what branches are, when and how to use them, and how to deal with merge conflicts. Admittedly, some of these concepts can get pretty tricky. So we really recommend that you follow along on your computer, experiment with the commands that we show, and try things on your own until you feel comfortable with these techniques. Remember that you can always go back and review any earlier videos if something isn't totally clear. If after all this you still feel stuck, be sure to use the discussion forums to ask for help as well. So are you ready to learn more about advanced features in Git? Let's get to it! When we covered the basic Git workflow, we called out that the process is usually to make changes, stage them, and then commit them. The separate step between staging and committing allows us to stage several changes in one commit. But if we already know that the current changes are the ones that we want to commit, we can skip the staging step and go directly to the commit. No dress rehearsals. We do this by using the -a flag to the git commit command. This flag automatically stages every file that's tracked and modified before doing the commit, letting us skip the git add step. At first, you might think that git commit -a is just a shortcut for git add followed by git commit. But that's not exactly true. Git commit -a doesn't work on new files because those are untracked. Instead, git commit -a is a shortcut to stage any changes to tracked files and commit them in one step. If the modified file has never been committed to the repo, we'll still need to use git add to track it first. So, let's make a change to our example script from an earlier video and try out this new flag. We'll now modify our main function and make it call the check reboot function that we wrote before. If a reboot is pending, we'll print a message and then exit our program with an exit status of 1. And since we're using the sys module, we'll need to import it. All right, now that we've made the change, we're ready to try out the new -a flag. We'll also use the -m flag to add the commit message directly. This time, we'll say that we're calling check_reboot and exiting with 1 on the error condition. Success! These shortcuts are useful when making small changes that we know we'll want to commit directly without keeping them in the staging area and having to write long and complex descriptions. Keep in mind that when you use the -m shortcut, you can only write short messages and can't use the best practices regarding commit descriptions that we talked about earlier. So, it's best reserved for truly small changes that don't require extra context or explanation. Short and sweet. Heads up, when you use the -a shortcut, you skip the staging area, meaning you can't add any other changes before creating the commit. So you need to be sure that you've already included everything you want to include in that commit. In the end, using a shortcut like -a is just like using the regular commit workflow. The commit will show up in the log along with the message just as usual. Let's check that out. See how our latest commit was added to the top of the list of commits? And notice how the head indicator has now moved to the latest commit? You might be wondering, what is this head and where is it heading? We'll keep coming across it, so let's clarify. Git uses the head alias to represent the currently checked out snapshot of your project. This lets you know what the contents of your working directory should be. In this case, the current snapshot is the latest commit in the project. We'll soon learn about branches, and in that case, head can be a commit in a different branch of the project. We could even use Git to go back in time and have head represent an old commit from before the latest changes were applied. In all cases, head is used to indicate what the currently checked out snapshot is. This is how Git marks your place in the project. Think about it as a bookmark that you can use to keep track of where you are. Even if you have multiple books to read, the bookmark allows you to pick up right where you left off. When you run Git commands like diff, branch, or status, Git will use the head bookmark as a basis for whatever operation it's performing. We'll see head used when we learn how to undo things and perform rollbacks, and we'll talk more about branches in later videos. As a shortcut, it's generally easy to think of head as a pointer to the current branch, although it can be more powerful than that. Up next, we'll dig into how we can get more information about our changes both before and after we commit them. We've seen how Git log shows us the list of commits made in the current Git repository. By default, it prints the commit message, the author, and the date of the change. This is useful, but if we're combing through a history of changes in a repo to try and find what caused the latest outage, we'll probably also need to look at the actual lines that changed in each commit. To do this with Git log, we can use the -p flag. The P comes from patch, because using this flag gives us the patch that was created. Let's try it out. The format is equivalent to the diff-u output that we saw in an earlier video. It shows added lines with pluses and removed lines with dashes. Because the amount of text is now longer than what fits on your screen, Git automatically uses a paging tool that allows us to scroll using page up, page down, and the arrow keys. We still have one commit below the other, but now each commit takes up a different amount of space, depending on how many lines were added or removed in that commit. Using this option, we can quickly see what changes were made to the files in our repository. This can be especially useful if we're trying to track down a change that recently broke our tools. If we don't want to scroll down until we find the commit that we're actually interested in, another option is to use the git show command. This command takes a commit ID as a parameter and will display the information about the commit and the associated patch. We'll talk more about commit IDs in a later video, but for now, remember that this is an identifier that we see next to the word commit in the log. Let's check this out by first listing the current commits in the repo and then calling git show for the second commit in the list. First, I'm going to exit out by pressing Q. We've shown how we can use git log for listing commits and git log-p for showing the associated patches. Another interesting flag for git log is the --stat flag. This will cause git log to show some stats about the changes in the commit, like which files were changed and how many lines were added or removed. Let's try it with our repo. There are a bunch of other options to git log, so we won't cover them all. You can always use the reference documentation or the manual pages to find out more. And, as we called out before, you don't need to memorize any of this. You'll learn the different commands and flags by using them. The important thing to remember is that all the information is stored in the repository and you have it at your fingertips when you need it. You're welcome. Now, what about changes that haven't been committed yet? Until now, whenever we've made changes to our files, we've either added them to the staging area with git add and committed them with git commit, or committed them directly using git commit-a. This works fine, but it means we have to know exactly which changes we've made. Sometimes it can take a while until we're ready to commit. We call these commitment issues. Just kidding. But imagine you've been working on adding a new complex feature to a script and it requires thorough testing. Before committing it, you need to make sure that it works correctly. check that all the test cases are covered, and so on and so on. So while doing this, you find bugs in your code that you need to fix. It's only natural that by the time you get to the commit step, you don't really remember everything you've changed. To help us keep track, Git gives us the git diff command. Let's make a new change to our script and then try this command out. We'll add another message to the user to say that everything is okay when the check is successful, and then exit with 0 instead of 1. Okay, we've made the change. Let's now save it and check out what git diff shows us. Again, this format is equivalent to the diff-u output that we saw in an earlier video. In this case, we see that the only change is the extra lines that we've added. If our change was bigger and included several files, we could pass a file by parameter to see the differences relevant to that specific file, instead of all the files at the same time. Something else we can do to review changes before adding them is to use the -p flag with the git add command. When we use this flag, Git will show us the change being added and ask us if we want to stage it or not. This way, we can detect if there's any changes that we don't want to commit. Let's try that one out. We've staged our change and it's now ready to be committed. If we call git diff again, it won't show any differences, since git diff shows only unstaged changes by default. Instead, we can call git diff -- staged to see the changes that are staged but not committed. With this command, we can see the actual staged changes before we call git commit. Let's commit these changes now so that they aren't pending anymore. We'll say that we've added a message when everything is okay. Nice. And with that, we've learned a bunch of different ways to get more information about our changes. We've covered a lot of ground, so take the time to review and practice these commands if they don't make sense yet. Up next, we'll look into what happens when we want to delete or rename files in our repository. It's time to do a little housekeeping. Let's say that you've decided to clean up some old scripts and want to remove them from your repository. Or you've done some refactoring, which makes a particular file obsolete. You can remove files from your repository with the git rm command, which will stop the file from being tracked by Git and remove it from the Git directory. File removals go through the same general workflow that we've seen, so you'll need to write a commit message as to why you've deleted them. Let's try this out in our checks repository that contains a file we decided we actually don't want. We'll first look at the contents of the directory with ls, then delete the file with git rm, then check the contents with ls again, and finally check the status with git status. So, we see that by calling git rm, the file was deleted from the directory, and the change was also staged to be committed in our next commit. Let's do that now by calling git commit and setting a message indicating that we've deleted the unneeded file. As usual, we get a bunch of stats when we do the commit. Check out all the deletions it reported. These are all lines in the file that are no longer there, and it states that the file itself was deleted. What if you have a file that isn't accurately named? This can happen. For example, if you start writing a script that you thought would only do one thing and then expands to cover more use cases, or conversely, if you named your script thinking that it would be very generic, but it ends up being more specific. You can use the git mv command to rename files in the repository. Let's rename our existing script to checkfreespace.py and then check what git status has to say about that. The status shows us that the file was renamed and clearly displays the old and new names. As with the previous example, the change is staged but not committed. Let's commit it by calling git commit once again. The git mv command works in a similar way to the mv command on Linux. and so can be used for both moving and renaming. If our repository included more directories in it, we could use the same git mv command to move files between directories. As you can probably tell from our examples, the output of git status is a super useful tool to help us know what's up with our files. It shows us which files have tracked or untracked changes, and which files were added, modified, deleted, or renamed. It's important that the output of these commands stays relevant to what we're doing. If we have a long list of untracked files, we might lose an important change in the noise. If there are files that get automatically generated by our scripts, or our operating system generates artifacts that we don't want in our repo, we'll want to ignore them so that they don't add noise to the output of git status. To do this, we can use the git ignore file. Inside this file, we'll specify rules to tell Git which files to skip for the current repo. For example, if we're working on an OS X computer, we'll probably want to ignore the .dsstore file, which is automatically generated by the operating system. To do this, we'll create a .gitignore file containing the name of this file. Remember that the dot prefix in a Unix-like file system indicates that the file or directory is hidden and won't show up when you do the normal directory listing. That's why we have to use ls-la to see all files. We've added a gitignore file to our repo, but we haven't committed it yet. This file needs to get tracked just like the rest of the files in the repo. Let's add it now. Looks great. We've learned a lot of new commands and techniques related to Git in these past videos. If anything isn't clear at this point, now is a good time to experiment on your own and share any challenges in the discussion forums. Being able to revert our changes is one of the most powerful features offered by version control systems. And there's a bunch of different techniques available depending on which changes we need to undo. In this video and the next few coming up, we'll talk about the most common ways to revert changes in Git and when to use each approach. For example, you might find yourself in a situation where you've made a bunch of changes to a file, but decide that you don't want to keep them. You can change a file back to its earlier committed state by using the git checkout command, followed by the name of the file you want to revert. Speaking of, let's try this out using our scripts repository. We'll edit our allchecks.py script and remove the check reboot function, then save and go back to the command line. Cool, we've made our change. Let's try our script and see what happens. Oof. By deleting that function, we've actually broke the script. Let's see what git status has to say about this. As expected, we see that our file is modified and the changes aren't staged yet. Check out how Git gives us a couple helpful tips on what to do now. We can run git add to stage our changes, or we can run git checkout to discard them. If you need help remembering what this command does, think of it this way. You're checking out the original file from the latest stored snapshot. Let's do that now. We'll check out at the original file and then take a look at what git status has to say about it, and finally retry our script. Oops, looks like we have a typo. Let's go back and fix it. Done and done. With that, we've demonstrated how we can use git checkout to revert changes to modified files before they get staged. This command will restore the file to the latest stored snapshot, which can be either committed or staged. So, if you've made additional changes to a file after you've staged it, you can restore the file to the earlier staged version. And if you need to check out individual changes instead of the whole file, you can do that using the -p flag. This will ask you change by change if you want to go back to the previous snapshot or not. Okay, that's it for undoing unstaged changes. But what if you added the changes to the staging area already? Don't stress. If we realize we've added something to the staging area that we didn't actually want to commit, we can unstage our changes by using the git reset command. Staging changes that we don't actually intend to commit happens all the time, especially if we use a command like git add star, where the star is a file glob pattern used in bash that expands to all files. This command will end up adding any change done in the working tree to the staging area. And while sometimes that might be what we want, it can also lead to some surprises. Let's try it out with an example. First, we'll pretend we're trying to debug a problem in our script. And for that, we create a temporary file with the output of our script. Then, we'll add all unstaged changes in our working tree using git add star. And finally, check the status using git status. We can see that this output file, which was supposed to be a temporary file for debugging, has now been staged in our repo, but we didn't want to commit it. Conveniently, the git status command tells us how to unstage the file right there in the output. The example output mentions the head alias. Remember what that means? That's right. It's the current checked out snapshot. So, by running the suggested command, we're resetting our changes to whatever's in the current snapshot. Let's try it out. Ta-da! The file is once again untracked in our working tree and no longer staged. You can think of reset as the counterpart to add. With add, you can, well, add changes to the staging area. With reset, you remove changes from the staging area. And you can use git reset-p to get Git to ask you which specific changes you want to reset. Get it? But wait, let's remember to commit our typo fix. With that, we've seen how we can revert unstaged and staged changes. But what if you've already created a commit with the changes that you want to undo? Great question. That's coming up in the next video. In general, we try to make sure our commits include all the right changes and descriptions. But we're all human, and we make mistakes. It's not uncommon for developers and IT specialists to realize that there is an error in a recent commit, which is why it's important to know how to take action and fix it. Let's say you've just finished committing your latest batch of work, but you've forgotten to add a file that belongs to the same change. You'll want to update the commit to include that change. Or maybe the files were correct, but you realize that your commit message just wasn't descriptive enough. So you want to fix the description to add a link to the bug that you were solving with that commit. What can you do? We can solve problems like these using the --amend option of the git commit command. When we run git commit --amend, Git will take whatever is currently in our staging area and run the git commit workflow to overwrite the previous commit. Let's see this in an example. We'll go to our scripts directory and create 2 new files using the touch command. Then list the content of the directory using ls, add our Python script, and commit it saying that we've added 2 files. As you can see, the message printed by Git says that only 1 file was added. Our commit message said that we added 2 files, but we forgot to add one of them. Ouch. Don't panic, we can fix it. We'll start by adding the missing file and then amending our commit. We called git commit --amend and an editor opened up showing the commit message and the stats about the commit that we're working with. The list of added files for this commit now includes both files that we wanted to add. Yay! Now that the files have been added, we can also improve our initial commit message, which was a bit too short. We'll keep the existing description as the first sentence of our commit, and then add a line of description about the intended purpose of each file. Okay, with that, our commit is ready to be amended. Let's save the new description as usual. Woohoo! We've amended our previous commit to include both files and a better message. You could also just update the message of the previous commit by running the git commit -- amend command with no changes in the staging area. An important heads up, while git -- amend is okay for fixing up local commits, you shouldn't use it on public commits, meaning those that have been pushed to a public or shared repository. This is because using -- amend rewrites the git history, removing the previous commit and replacing it with the amended one. This can lead to some confusing situations when working with other people and should definitely be avoided. So remember, fixing up a local commit with amend is great, and you can push it to a shared repository after you fixed it, but you should avoid amending commits that have already been made public. If this sounds confusing now, don't worry. We'll mention it again when we talk about collaborating with others through shared repositories. Okay, we've covered how to fix staged and unstaged changes, and how to fix a commit that was incomplete. Up next, we'll talk about what to do if you come across a bad commit that needs to be completely reverted. Fixing your work before you commit is good, but what happens if it's already been snapshotted by Git? Let's say you host a Git repository on a company server that contains all kinds of useful automation scripts that you and your coworkers use. One morning before coffee, you make a few changes to one of these scripts and commit the updated files. A few hours later, you start to receive tickets from users indicating some part of the script is broken. From the errors they describe, it sounds like the problem is related to your recent changes. Uh-oh. You could look at the code you updated to see if you can spot the bug, but more tickets are pouring in and you want to fix the problem as fast as possible. You've decided it's time for a rollback. There are a few ways to roll back commits in Git. For now, we'll focus on using the git revert command. In Git, revert doesn't just mean undo. Instead, it creates a commit that contains the inverse of all the changes made in the bad commit in order to cancel them out. For example, if a particular line was added in the bad commit, then in the reverted commit, the same line will be deleted. This way, you get the effect of having undone the changes, but the history of the commits in the project remains consistent, leaving a record of exactly what happened. So, git revert will create a new commit that is the opposite of everything in the given commit. We can revert the latest commit by using the head alias that we mentioned before. Since we can think of head as a pointer to the snapshot of your current commit, when we pass head to the revert command, we tell Git to rewind that current commit. Make sense? To check this out, we'll first add a faulty commit to our example repo. Okay, we've added some code to our script. Let's save and commit this. So now our code is committed. We didn't even test it, which is a bad idea if you're doing this for real. And you might have already spotted the problem with our code. This is where our users start filing tickets and saying that things are broken. And so we run our script to see what happens. Oops. We used a function that we forgot to define. Okay, it's rollback time. Let's get rid of this faulty code by typing git revert head. So, once we issue the git revert command, we're presented with the text editor commit interface that we've all seen before. In this case, we can see that Git has automatically added some text to the commit, indicating it's a rollback. The first line mentions that it's reverting the commit we just did called add call to disk full function. The extra description even includes the identifier of the commit that got reverted. While we could use this description as is, it's usually a good idea to add an explanation of why we're doing the rollback. Remember that the goal of these descriptions is to help our future selves understand why things happened. In this case, we'll explain that the reason for the rollback is that the code was calling a function that wasn't defined. Once we're done entering the description, we can exit and save as usual. You'll notice the output that we get from the git revert command looks like the output of the git commit command. This is because git revert creates a commit for us. And since a revert is a normal commit, we can see both the commit and the reverted commit in the log. Let's look at the last two entries in the log using -p and -2 as parameters. As demonstrated before, the -p parameter lets us see the patch created by the commit, while the -2 parameter limits the output to the last two entries. So, in this log, we can see that when we called revert, Git created a new commit that's the inverse of the previous one. This removes the lines that we added in the previous commit. We can see that the original commit shows the lines we added by preceding them with a plus sign. The same line shows up with a minus sign in the newer commit message, indicating that they were removed. Just like that, the bad commit is reverted and the errors stop. Phew! In this example, we reverted the latest commit in our tree. But what if we had to revert a commit that was done before that? Rev up your time machines, because in the next video, we're turning back the clock big time. So far, we've used the head alias to specify the most recently checked out commit in our Git history. In our bad snapshot example, the error also happened to be in the most recently created commit, but errors can sometimes take a while to be detected. And so we might need to revert other commits farther back in time. We can target a specific commit by using its commit ID. We've seen commit IDs a few times already. They show up when we're running the git log command, and we also saw the commit ID of the reverted commit in our last example. Commit IDs are those complicated looking strings that appear after the word commit in the log messages. Let's have a look at the latest log entry in our checks repo. The commit ID is the 40-character long string after the word commit. You really can't miss it. This long jumble of letters and numbers is actually something called a hash, which is calculated using an algorithm called SHA-1. Essentially, what this algorithm does is take a bunch of data as input and produce a 40-character string from the data as the output. In the case of Git, the input is all information related to the commit, and the 40-character string is the commit ID. Cryptographic algorithms like SHA-1 can be really complex, so we won't go too deep into what this means. If you're interested, you'll find links to more information in the next reading. Still, you might be wondering, why on earth would you use a long jumble of letters as an ID for a commit, instead of incrementing an integer like 1, 2, 3, etc.? To answer that, let's take a quick look at the reason why Git uses a hash instead of a counter, and how that hash is computed. Although SHA-1 is a part of the class of cryptographic hash functions, Git doesn't really use these hashes for security. Instead, they're used to guarantee the consistency of our repository. Having consistent data means that we get exactly what we expect. To quote Git's creator Linus Torvalds, you can verify the data you get back out is the exact same data you put in. This is really useful in distributed systems like Git, because everyone has their own repository and is transmitting their own pieces of data. Computing the hash keeps data consistent because it's calculated from all the information that makes up a commit: the commit message, date, author, and the snapshot taken of the working tree. The chance of two different commits producing the same hash, commonly referred to as a collision, is extremely small. So small, it wouldn't happen by chance. It'd take a lot of processing power to cause this to happen on purpose. If you use a hash to guarantee consistency, you can't change anything in the git commit without the SHA-1 hash changing too. Remember our discussion about fixing commits with the --amend command? Each time we amend a commit, the commit ID will change. This is why it's important not to use --amend on commits that have been made public. The data integrity offered by the commit ID means that if a bad disk or network link corrupts some data in your repository, or worse, if someone intentionally corrupts some data, Git can use the hash to spot that corruption. Aha, it will say, the data you've got isn't the data you expected. Something went wrong. Thank you, Detective Git. You've saved the day once again. Okay, enough backstory. How can you use commit IDs to specify a particular commit to work with, like during a rollback? Let's look at the last 2 entries in our repo using the git log-2 command. Say we realize that we actually like the previous name of our script, and so we want to revert this commit where we renamed it. First, let's look at that specific commit using git show, which we mentioned in an earlier video. We've copied and pasted the commit ID that we wanted to display, and that works. Alternatively, we could provide just the first few characters identifying the commit to the command, and Git will be smart enough to guess which commit ID starts with those characters, as long as there's only one matching possibility. Let's try this out. Two characters is not enough, but usually 4 to 8 characters will be plenty. Okay, now that we've seen how we can identify the commit that we want to revert, let's call the git revert command with this identifier. As usual, this will open an editor where we should add a reason for the rollback. In this case, we'll say that the previous name was actually better. Hooray for flip-flopping! As we called out before, when we generate the rollback, Git automatically includes the ID of the commit that we're reverting. This is useful when looking at a repo with a complicated history that includes a lot of commits. Now, once we save and exit the commit message, Git will actually perform the rollback and generate a new commit with its own ID. See how before the name of our commit, the revert command already shows the first 8 characters of the commit ID? Let's use git show to look at it. All right, we've managed to revert a commit that wasn't the most recent one. Well done, time travelers. Over the past several videos, we've covered a bunch of ways to undo things in Git, whether for unstaged changes, staged changes, amending commits, or rolling back changes. If anything still seems unclear, now's a great time to practice these commands on your local computer, try things out, and come up with more examples of use cases you want to test. Up until now, we've only briefly mentioned branches. You might have seen the text on branch master in commit messages, or you might remember that we talked about branches in the context of the head pointer. Branches are an important part of the Git workflow, so we'll branch out and explore them more thoroughly in the coming videos. So what is a branch, and what is it used for? In Git, a branch at the most basic level is just a pointer to a particular commit. But more importantly, it represents an independent line of development in a project, of which the commit it points to is the latest link in a chain of development history. The default branch that Git creates for you when a new repository is initialized is called master. All of our examples and development have taken place on this branch so far. The master branch is commonly used to represent the known good state of a project. When you want to develop a feature or try something new in your project, you can create a separate branch to do your work without worrying about messing up this current working state. If this seems confusing, maybe an analogy will help. You can think of a Git project as an assignment your teacher gives you in a class. You do all your work on the assignment in a set of notebooks, each notebook representing a different branch. You use some notebooks to jot down rough drafts and experiments, but you keep one notebook, the master branch, in a tidy state, and you copy the polished versions of these drafts into it. No doodling in the master notebook, please. Branches make it really easy to experiment with new ideas or strategies in projects. When you want to add a feature or fix something, you can create a new branch and do your development there. You can merge back into the master branch when you've got something you like, or discard your changes without negative impact if they don't work out. In Git, branches are used all the time as a part of the normal development workflow. As an example, think back to the problematic commit we fixed in an earlier video. We added a call to the disk full function, but forgot to actually define the function. So we had to roll it back because our users were seeing errors. Knowing what we know now, we could have done that work on a separate branch, maybe called something like add disk full. In that case, we could have iterated on our code there until it was working correctly without it affecting the master branch. Only after the code was ready to be deployed, we would merge those changes back into the master branch. In the next few videos, we'll look into how to create new branches and merge their content into the master branch. We'll also go over what to do if you run into any scary merge conflicts. Heads up, this is about to get pretty complicated, so make sure that you follow all of our exercises along on your computer, and keep practicing coming up with new ways of using branches and merging until you're comfortable with each of the steps we show. As branches are essential to how work is done in Git, there's tons of different ways to work with them. We can use the git branch command to list, create, delete, and manipulate branches. Running git branch by itself will show you a list of all the branches in your repository. Let's try it out in our checks repo. Our list is looking pretty empty right now, but don't worry, creating a branch is a snap. We do it by calling git branch with the name of the new branch. Let's create a new feature branch and then list the branches again with git branch. Our new branch was created based on the value of head. Remember that this might not necessarily be the master branch. The list we get shows that we're still on the master branch. We can tell because the current branch is indicated in the command's output with an asterisk in a different color. We'll look into other things that git branch lets us do with branches later on, but right now we want to switch to a new branch. To do that, we'll need to use the git checkout command. We saw earlier how we can use git checkout to restore a modified file back to the latest commit. Checking out branches is similar in that the working tree is updated to match the selected branch, including both the files and the git history. If this seems a bit confusing at first, you are not alone. I also found it hard to wrap my head around at first, but rest assured that it will become clearer after we use these commands for a while. It might help to remember that we use git checkout to check out the latest snapshot for both files and for branches. All right, let's switch to our new feature branch by calling git checkout new feature and then listing our branches once again. Before, we were working on the master branch, but now that we've changed to our new branch, the star has moved to new feature. Creating a branch and switching to it immediately is a pretty common task. So common that Git gives us a useful shortcut to create a new branch and to switch to it in a single command. We can use the git checkout-b new branch to do this. Take a look. See how the message says that we've switched to a new branch? Git created the new branch and switched to it in just one command. Super efficient, right? All right, now that we have our shiny new branch, let's create a new file in it. We'll create a new Python 3 file that will include the usual shebang line, an empty main function, and a call to that function. This file is empty because it's only the beginning of our work. As it's in a separate branch, it's okay for it to not be finished yet. Let's save our file and commit it to the current branch now. All right, we've added a commit in this branch and it's looking better. Let's check the last two entries in the log. We see the last two commits in this branch. Notice how next to the latest commit ID, Git shows that this is where head is pointing to, and that the branch is called even better feature. And next to the previous commit, Git shows that both the master and the new feature branches are pointing to that snapshot of the project. In this way, we can see that the even better feature branch is ahead of the master branch. With that, we've seen how we can create new branches and commit changes to them. You might say your knowledge of branches has grown. Up next, we'll learn even more things we can do to operate with branches. So stick around. Let's check out the current status of our repo by calling git status and ls-l. So, we see that we're on a clean working tree in the even better feature branch, and that the new free memory py file is in our working tree. Let's now change back to the master branch using git checkout master, and then list the latest two commits there. When we switch to a different branch using git checkout, under the hood, Git changes where head is pointing. Thanks to this checkout, head went from pointing to the latest commit in the even better feature branch to the most recent commit of the master branch. The commit from even better feature doesn't show up at all, and the latest snapshot is the second entry we've seen before. Remember that when we switch branches, Git will also change files in our working directory or working tree to whatever snapshot head is currently pointing at. Let's look at the current contents of our directory. Whoa. Free memory py isn't there. This demonstrates that when we switch branches in Git, the working directory and commit history will be changed to reflect the snapshot of our project in that branch. When we check out a new branch and commit on it, those changes will be added to the history of that branch. Since free memory py was committed on another branch, it doesn't show up in the history or working directory of the master branch. One thing to note after all this back and forth is that each branch is just a pointer to a specific commit in a series of snapshots. It's very easy to create new branches because there isn't any data that needs to be copied around. When we switch to another branch, we check out a different commit and Git updates both head and the contents of our working directory. Head floats around with us. It's like a free spirit. What a head trip. Okay, we've now seen how to create and switch between branches. So what if we want to delete a branch that we don't need anymore? We can do that by using git branch-d. Let's first list the current branches in our repo, and then get rid of the new feature branch by calling git branch-d new feature. And just like that, our branch was trimmed. We can check with another call to git branch that is not there anymore. If there are changes in the branch we want to delete that haven't been merged back into the master branch, Git will let us know with an error. Helpfully, Git also gives us the command to run if we were sure that we wanted to delete the branch, even if it has unmerged changes. But we won't do that just yet. We actually want to merge those changes back into the repo first. And how do we do that? A typical workflow for managing branches in Git is to create a separate branch for developing any new features or changes. Once the new feature is in good shape, we merge the separate branch back into the main trunk of code. Merging is the term that Git uses for combining branch data and history together. We'll use the git merge command, which lets us take the independent snapshots and history of one Git branch and tangle them into another. Let's try this out with our example branch from the last video. First, we'll check that we're in the master branch, and then we'll call git merge even better feature to merge the even better feature branch into the master branch. Now we've brought the master branch up to speed, which we can see by looking at the Git log. As we're on the master branch, head points at master. We can see the even better feature and master branches are now both pointing at the same commit. Git uses two different algorithms to perform a merge: fast forward and three-way merge. The merge we just performed is an example of a fast-forward merge. This kind of merge occurs when all the commits in the checked out branch are also in the branch that's being merged. If this is the case, we can say that the commit history of both branches doesn't diverge. In these cases, all Git has to do is update the pointers of the branches to the same commit, and no actual merging needs to take place. On the other hand, a three-way merge is performed when the history of the merging branches has diverged in some way, and there isn't a nice linear path to combine them via fast forwarding. This happens when a commit is made on one branch after the point when both branches split. In our case, this could have happened if we made a commit on the master branch after creating the other branches. When this occurs, Git will tie the branch histories together with a new commit and merge the snapshots at the two branch tips with the most recent common ancestor, the commit before the divergence. To do this successfully, Git tries to figure out how to combine both snapshots. If the changes were made in different files or in different parts of the same file, Git will take both changes and put them together in the result. If, instead, the changes were made on the same part of the same file, Git won't know how to merge those changes, and the attempt will result in a merge conflict. This sounds scary, but don't panic. Git doesn't quit. From time to time, we might find that both the branches we're trying to merge have edits to the same part of the same file. This will result in something called a merge conflict. Normally, Git can automatically merge files for us, but when we have a merge conflict, it will need a little help to figure out what to do. To see how this would look, let's edit the free memory pie file in the master branch and replace the pass statement with a comment about what the main function should do. Cool, we made the change, so let's save it and commit it back to our master branch. Next, let's check out the even better feature branch and make a change in the same place. In this case, we'll replace the call to pass with a call to print, saying that everything is okay. Now we'll save this other change and commit it to this branch. We are primed for chaos with our file all set up for our merge conflict. Let's check out the master branch again and try to merge the even better feature back into it. Git tells us it tried to automatically merge the two versions of the free memory file, but it didn't know how to do it. We can use git status to get more information about what's going on. As usual, git status gives us a lot of additional information. It tells us that we have files that are currently unmerged and that we need to fix the conflicts or abort the merge if we decide it was a mistake. It also tells us that we need to run git add on each unmerged file to mark that the conflicts have been resolved. So let's get to work. To fix the conflict, let's open up free memory pie in our text editor. Thankfully, Git has added some information to our files to tell us which parts of the code are conflicting. The unmerged content of the file at head, remember, in this case head points to master, is the doc string stating what the main function should do. And the unmerged content of the file in the even better feature branch is the call to the print function. So it's up to us to decide which one to keep, or if we should change the contents of the file altogether. In this case, we'll keep both statements and delete the merger markers. Now that we've fixed the conflict, we'll mark it as resolved by running git add on the file, and then call the git status to see how our merge is doing. See how git now tells us that all conflicts have been resolved? Woohoo! We just need to call git commit to wrap up the merge. The comments that git commit shows us look different than other commits. That's because this is a merge, and git tells us so. It also tells us which file had conflicts, which have now been resolved. The commit already has a description saying that it's merging the other branch. This description was automatically created when we called the git merge command, but we can add onto this description if we want. For example, we can say that we're keeping the lines from both branches, and then just save and exit as usual. And the merge conflict is resolved. To see what the commit history looks like now, we'll use a couple of handy options to the git log command. --graph for seeing the commits as a graph, and --one line to only see one line per commit. This format helps us better understand the history of our commits and how merges have occurred. We can see the new commit that was added and also the two separate commits that we merged, one coming from the master branch and the other coming from the even better feature branch. We can also see that master is pointing to the merge commit, but even better feature is still pointing to the previous one. In our example, resolving the conflict was straightforward and easy. But in the real world, this won't always be the case. Merge conflicts can sometimes be tricky, complicated, and spread across multiple files. If you want to throw the merge away and start over, you can use the git merge --abort command as an escape hatch. This will stop the merge and reset the files in your working tree back to the previous commit before the merge ever happened. So, by now you know how to create, delete, and switch between branches in Git. You've also seen that each branch represents a pointer to a commit and a sequence of independent snapshots. And you know how to merge these commits back into the main trunk by using the git merge command. Amazing work! Seriously, this isn't easy stuff.
Congratulations on finishing this lesson in the Google IT Automation with Python certificate. Access the full experience, including job search help, and get the official certificate by clicking the icon or the link in the description. Watch the next lesson in the course by clicking here, and subscribe to our channel for more lessons from upcoming Google Career Certificates.